Yes, energy diagnostics investigator for efficiency savings.
Can you say it here?
So where are you from?
Okay.
There you go.
Okay, there you go. So I'm going to talk about the Edifes project, which is the energy efficiency project that we have done in Case Western Reserve University. And the project was funded, it's a 3-year project funded by ARPA. The project it was over actually in April, but then they extended like for 8 more months to just make the API ready for commercializing this product. So what is Edifes? First of all, why Edifes is important? Because we know, like, you might even know more than me because I came from stats background. So 40% of the energy consumption in the US is for the commercial buildings. And we know, like, most of these buildings are dumb. It means, like, they have the potential for energy savings. So, and we know, like, submetering the data set, traditional auditing of the buildings are really costly and cumbersome. So that's why we need a product to virtually audit the building energy efficiencies, and that's Edifes. So what Edifes is we have 4 stages in Edifes. First one is diagnosing the building characteristics using the diagnostic markers that we have. After that, in the prognostic stage, we specify the energy efficiency and the potential of the savings in each specific building, and then compare it with the population of the buildings that we have and tell the building owner how their building behaves compared to the other buildings in the same building type. And after that, if the building owners, or so assuming like they have multiple buildings, like some food services that they have multiple branches, or retail stores that have multiple branches, we can screening their buildings and ranking their buildings based on the savings opportunity that they have. So how do we do this? So the only information we get from the building owners is at least 1 year of energy consumption from the smart meters, which are mainly 15 minutes interval data set. We have even some buildings with like 1 minute interval or 30 minutes interval consumption. And just keep in mind, like, these are the whole building energy consumption, not sub-meters. And we also get the location of the building from the zip code or the address that the building owner provided for us, and the size of the building, the square footage of the building. These are the only information we get from the building owners. And then we identify the energy savings opportunity for their buildings. Now the question is how we do this. So we basically do lots of rigorous analysis, statistical analysis, combine this data set with the weather variables that we know they are really affect the energy consumption of the buildings. And based on the location, we can find the climate zones. So we got the data set from almost 2,000 buildings from different buildings, different partners in North America that we have. And like also they call it smart meters, but still like any other real data set, we had like anomalies, we had missing points. We took care of all of those, like detect the anomalies, impute those. And we had even like chunk of missing points that we impute them with the prediction methods that we have. And then after restructuring the data set, tightening the data set, we store the raw data set in HDFS, and then the clean data set in the HBase on top of the HDFS. And we also get the weather variables from another source, SolarGIS, that we have access to for North America, and store all of the information of this in the meta table using the RedCat. So basically, we use the Cradle that we have at Case Western Reserve University to do all of these analysis. And that's just a picture of the Cradle that we have. We have like 4,000 compute cores with almost 110,000 of GPU cores, and we are able to use either R or Python to call the data sets and do the analysis on Cradle. This is the distribution of the buildings that we have in US. So as you can see, unfortunately, we don't have many buildings in the center of the North America, and we are really willing to get like those buildings from those areas as well. We are still looking for partners and make the population of the buildings that we have larger and larger that increase the accuracy of this product. So let's see like what's the snapshot of like the consumption of one of these buildings. So this is like what we call it a snapshot of the building. It's actually really informative. Like on the top, we have the side-by-side box plots for 24 hours of the consumption for the whole year that we have. And then in the second row, we have just the winter consumption compared with the summer one. So like, for example, why I say this plot is really informative, also it's pretty simple. It's just like it's visualization of this build, the consumption without doing any analysis on it. But still we can see that, like, for example, this building is really unoccupied on the Saturday and Sunday compared to the weekdays. We can see the consumption during the winter is pretty much lower than the consumption during the summertime, which means like they have another source for heating up the building. That's a gas. We just get the electricity consumption. And we also can see the variability of the consumptions that we have, which shows like this blue area that we have here. That's like the interquartile range of the data set that we have for each hour. And that shows like the variability of the turning on and off of the equipments, which are mainly the HVAC during the daytime for the buildings. So this is the list of almost like 15 of the markers that we developed. We developed 40 different building markers, but obviously there's no space and time to present all of these markers that we developed. Each one of the markers represents one of the characteristics of a building. It's either diagnostic or prognostic, which detects the characteristic of a building or reporting the savings opportunity of that building. For example, like we have some buildings to detect the HVAC schedule if the building has HVAC schedule, and then we have another marker to reschedule the HVAC system in the building. And then we have another marker to predict the saving opportunity of the changing the schedule of the HVAC. And then same thing with the plug load. We could disaggregate the plug load from the whole energy consumption. So like the exterior lights of the building. So I'm gonna cover just I choose just randomly couple of the markers today to present. Obviously, I don't have time even to present all of these 15 markers. And sorry, I don't want to skip this. It's like, this is like these plots are like the sample plots of the buildings that we report to the building owners. Sample plots of the energy efficiency, energy savings opportunity. Like, for example, like by this one on the left side, we can tell the building owner if they change the thermostat set point by just 2 degrees, how much energy they can save in the whole year. And some of these are like not even doing a retrofit into the building and doesn't cost anything. It's just rescheduling. But some of them, yeah, it's like, for example, if we detect their HVAC is oversized, then they need to reduce the size of the HVAC and, doing some, or if we detect like their HVAC is not working in the high efficiency, then they might need to replace that. That's actually cost effective for them. And the other one on the right side that I have is like window and R value of the building. So we detect like if the building has a good envelope, what's the shape of, what's the building envelope compared to the other buildings, and we usually compare it with the ASHRAE standard values, and then we detect that if the R value of the building is lower than the ASHRAE target value, how much energy they can save just to, if they achieve to that target value. So basically, since we wanted to predict the energy saving, then we need the baseline prediction for the energy consumption. We do this based on 2 different methods. We tried multiple different methods like SVM method or like neural networks, but so far these are the best one that works for us. The first one is diffusion index, and the second one is a random forest. Just if you're curious, what is the diffusion index? Diffusion index method is like a multivariate time series prediction method. We know like this energy consumption of a building, it's really highly correlated with the weather variables. So I don't have that plot here, but we all know like the energy consumption really depends on the temperature during the year, depends on the wind speed, GHI, and so since we have those data sets from the solar GIS, I use those data sets and combine it with the energy consumption and consider this as a multivariate time series, do the principal component analysis, find the best features, and then find the best model to predict the energy consumption in the next 6 months. I'm pretty sure most of you know what is random forest. I'm not going to go through the details of this method, but if anyone interested, I'll be really happy to discuss these things with you after that. But just keep in mind, like, for those who doesn't know, like random forest is like a multiple decision trees that we have, and so we try to optimize it based on minimizing the root mean square error of each one of the CART algorithms that we have to find the best method for the prediction of the energy consumption. And the features of the random forest is different from the features that we use in the diffusion index method. We use the one ad hoc method to generate the features of the random forest. And then now we need to check the accuracy of our prediction method. We check it based on the standard root mean square error and coefficient of variation of the standard root mean square error and mean biased error. But again, going back to the literature, we found this range of the acceptable value from this source. I believe it's ASHRAE or DOE, I don't know which one is it. But this is and as long as our prediction is within the 10% and 20 or 30% of the mean bias error or coefficient of variation of the root mean square error, we are good, based on the literature. So what we do is basically just before going to the building markers, so first of all, we use the building change event detector to detect if we have any significant change event in the building, which means like if the building has any retrofits, if the building had any retrofits before and we have the data set during the retrofit time, then we wanted to detect that retrofit time. And then we use the data set before the retrofit to predict the energy consumption after the retrofit, applying the retrofit that they had done. For example, if they replace their window and they said they replace the window by like replace a one layer window with triple layer, then we calculate the R value based on that and then apply the saving marker on the predicted value and compare the predicted of the energy consumption savings with the actual savings that they had. So I will show these things in the next couple of slides. First of all, as I said, we need to detect the retrofit time, change event detector. So we subset the data set into different years. If we have just 1 year of the data set, obviously there is no way for us to detect if there is a retrofit during that year or not, because it might be the effect of the variable, and it's hard to detect that's really effect of the weather variable or replacing an equipment. But if we have multiple years of the data set, we can compare we subset the data set to different years, and then apply the change event detector, find the time of the change point in each year, and if the time of the change point in different years are within 1 month of each other, that means and it's constant with the weather variable, with the weather change point actually, then that means that's an effect of the weather variable. Otherwise, it's highly possibly the retrofit in the building. Like, for example, this building. That's one of the buildings from the partners that we had. So we detected, using the change event detector, we detected a retrofit on May 2017, and then we asked the building owner, and they validate this. So basically, most of the functions that we have right now are validated at least based on 80 partners that we have. So what we did, we get the data set from them, we generate a report, return it back to them, and then they told us their feedback about like which one of the functions they think are correct and which one is not. So when we detected the change point, like the next one might be like building marker example of the HVAC scheduling. We take the derivatives of the data set and then find the significant changes into the derivatives and then plot these derivatives for each time of the day versus the date of the data set that we have. And we detected the turn based on the negative changes or positive changes. We can detect the turn on or off time of the HVAC schedule. For example, as we can see here on the left side, there is a range of the turn on point for this building during like almost 4:30 in the morning till 5:30 in the morning. That's the HVAC that turned on at that time. And then here in this one, we can see that there is we can see that two separate horizontal line that shows us two stages of the turn off time for the HVAC. And then after that, when we detected this, we can reschedule this. So we use the wavelet transformation to remove the noises, find the turn on and off time of the building, and then, so this red line is actually the removed noise one using the wavelet transformation, and then we try to reschedule it, like for example here by 30 minutes actually here, and to shift the turn on time 30 minutes earlier and, turn on time 30 minutes later and turn off time 30 minutes earlier. And then we add the noises back to the function and we can compare, then now the red one is the rescheduled building. And that's how we report this, like the total savings opportunity based on the shifting of 30 minutes, 60 minutes, or 90 minutes, shifting turn on and off time, and calculate the total savings that they can have for each specific building. And then, for example, this is one of the pilot partners that we have. It was a coffee shop, and it was a turn on time. We detected turn on time and turn off time are not aligned with the store hours. So they shifted the turn on time and turn off time, and then provided more data set after the rescheduling. So they did the rescheduling on December 2017, and then again provided the data set for us on September. And then we can compare the prediction method that we had. So this is like the validation, so I'm gonna skip this one. It's like the building a marker of the daylight sensors. So these are all the pilot partners that we have. And so we can compare like that for that building, we can compare like the actual savings versus the prediction savings that we have for each one of the building. That's actually the main purpose of doing the Edifes. And reporting the actual saving, comparing with the prediction saving. This is like the final screening tool that we have. It's like comparing the, like that was a retail store providing us, I think like 6 or 8 or 10 buildings, and then we rank order the buildings that they provided for us based on the saving opportunities that they had. So that's a basic screening tool that we have in Edifes for comparing different buildings for the same client. So this, as I said, this is a project that has been done by the HPC computers in Case Western Reserve University and funded by DOE ARPA project. Thank you.
Estimate the cost of these retrofits?
Actually, that's something that we don't want to do it at this step because we are not expert in like estimating those costs. But we are telling them, like in the plots that we reported to the building owners, we just say if you are able to reduce the plug load by like 10%, how much you can save. But we are not telling them at this step how you can do it. Okay.
How much efficiency can be achieved at what cost? I think it's hard to find.
Yeah, but some of them is like, for example, the HVAC reschedule. That's like mainly most of the building has like this match of the time aligns with the schedule of the building. Or we notice like some of the building doesn't have any schedule during the non-business days, which mainly they are unoccupied during that time, but they are not aware of that. So just based on rescheduling those things, without no cost, they can save energy.
I have 2 questions. Well, first, kind of related to the other, is that I actually agree. I think that's actually, would be really powerful to have. And I know it's a little outside of what you did, but I was wondering if you have thought of, as you go back to the building, saying, hey, can you fill out it, like what you spent, if you could, and then that could provide a base, because you're already speaking with them anyways, and that would provide a basis for the calculation. And then the other question that I had would be, so right now you're looking at coast to coast and you'd like to populate everywhere between. So if you were to populate everywhere between, clearly the climate and even coast to coast, the climate is going to make a big difference. So I saw we're seeing some climatic variables, but I'm wondering if you thought about that as you expand.
Yeah, that's one of the main things like we have in our mind. Like for example, for comparing the EUI of different buildings. So we know the EUI, it's highly dependent on the type of the building and the climate zone. So if we wanted to compare each specific building with the similar buildings, we need to have the population of the buildings in the same climate zone with the same building type. So we know like right now what we are doing is like using the clustering method, find the most similar ones, but we are really willing to get like buildings from the whole part of the North America. That's going to be the ideal case. And so we are still, by the way, we are still looking for the partner. So if anyone has anyone, knowing anyone, just let us know.
Very exciting. Of course, it's always the best if you have all the data you possibly can, especially in this case where you're running this little component analysis in the lake. But I do agree. I think that would be really interesting if you could get feedback.
Yeah, and right now we are working on like an API, making a dashboard that people can submit their just a CSV file of their data set. Then we get the data set, analyze it, and return back the report to them. That's what we are doing right now.